In the previous assignment, we motivated the dot product in vector spaces of functions based on dot products in three-dimensional space and general n-dimensional space. Here we take this analogy or idea further and develop an orthogonal basis for vector spaces of functions. So in three-dimensional space, let's say we have a vector v, and we have in function space, let's say we have functions in the interval 0 to t. A vector v is a function like this. The dot product in three-dimensional space is of two vectors, u1 v1 plus u2 v2 plus u3 v3. The analogous dot product of function spaces is the integral of the product of the functions. An orthogonal basis in three-dimensional space is the ijk. So if we dot them with each other, we get 0. If we dot them with themselves, we get 1. So what could be such an orthogonal basis for the function space? So consider the following set of functions. First is a constant of magnitude 1 over square root of t. Next, we take a sine and a cosine that make one cycle in the interval 0 to t, but their magnitudes are multiplied by square root of 2 over t. Then we take functions, sines and cosines that make two cycles, but again multiplied by square root of 2 over t. And then 3 cycles and 4 cycles and so on. We've shown already in a previous assignment that these functions, sines and cosines, when dotted with each other, give 0, so they are orthogonal. We can also verify that if we dot them with themselves, they give 1. In fact, the square root of 2 over t is so that when we dot them with themselves, we get 1. So in three-dimensional space, we can write a vector v as v1i plus v2j plus v3k. In the space of functions, most practical functions can be written in a similar way as coefficient times these basis functions. So a0 times the constant plus a1 times sine making one cycle, b1 times cosine making one cycle, a2 times cosine making two cycles, and so on. This is called Fourier series, and it's important to know that the Fourier series is an exact analog of simply writing v1i plus v2j plus v3k. Now, to find the coefficients in three-dimensional space, we would just dot the vector v with I, for example, to find the I coefficient, with j to find the j coefficient, with k to find the k coefficient. And this works exactly the same way with Fourier series. So to find the coefficient of the constant, we dot the function v with 1 over square root of t. To get the coefficient of the nth sine, we dot the function with the corresponding sine. To get the coefficient of the nth cosine, we dot it with the corresponding cosine. Now, functions can be approximated by a finite number of terms in the Fourier series. So instead of going to infinity, we'll go to just n, and this is a good way of constructing approximations for functions.